the universe was even more homogeneous close to the Big Bang. The temperature that you see in all directions hardly varies. And it was only in the early 90s that astronomers finally were able to measure the difference in temperature, which is what this map shows. The red shows the hot regions that are a little bit hot, and regions that blue is the regions that are a little bit cold. But the variation of temperature is 1 part in 10 to the 5, so 1 part in 100,000. So it basically hardly varies. Yeah? More or less you see the same temperature, but you do see tiny differences. Okay? And that was the achievement of an experiment called COBE. And then there's a follow-up experiment we call WMAP. Both of them are American experiments, and this is what that shows. So this, if you want, is a map of the stage of the universe, fairly close to the Big Bang. You might ask me how close, and this is the number. Close meaning 400,000 years. You might not be very impressed. 400,000 years is not that close, but compared to 13.7 billion years, this is when the universe was a baby. And this is what the universe looked like. Let me just explain a little bit about this ellipsoidal shape. You might wonder, what am I talking about? Is the universe like an egg or something? No, the universe is not like an egg. This is purely an artifact of the way we show the temperature variation in the universe. You should think of a map like this like when you look at the map of the world. Yeah? You know the world, the continents and the ocean is a two-dimensional surface, but usually you are familiar with a map of the world that is shown on a flat piece of paper. Usually there's some kind of projection done to make it ellipsoidal shape. Yes, you probably have seen that. This is done in the same way, exactly the same way. You got the idea? Except that what is shown here is not the map of the surface of the Earth, of course. It is showing a map of the temperature depending on where you are on the sky, which is also a two-dimensional surface if you think about it. That's what this is. Okay? So the universe back then was even more homogeneous compared to it is today. We do see a great confirmation that the universe was very hot. And the reason why we know it was very hot is because we see this light, which is the glow of the Big Bang. Today is very low temperature because these photons has cooled down. But if you go back then, the photons are at very high temperature. It was a very hot and dense Big Bang, indeed. Okay? And now let me try to explain to you the music that I showed at the beginning, okay? So, this is a stage of the universe today, and now, the way we like to kind of mathematically describe this pattern. Remember, one of our main goals in cosmology is to understand not only the pattern of the galaxies we see today, but also the pattern of this temperature variation on the sky, and in fact understand how you go from one to the other. Okay? And we need to find a way to analyze this pattern. And one primary way we analyze this pattern is to ask the following. You see, there are fluctuations basically in temperature on all scales. For example, if you go very close by, you see temperature varies. If you go very on large scales, you see another kind of variation. And what we would like to show, the way we analyze this data, is to plot the following. This is angular scale. This is large scale. This small scale, and this is the level of variation. So the way we like to analyze this, the technical term would be a Fourier transform. So we just like to say, what is the temperature variation as I look at points that are separated by different angles. For example, 90 angles, that's large scale, this is small scale. And we find the temperature fluctuation, the amplitude vary like this in a series of harmonics. And an astronomer had the bright idea of turning it into sound, which is what I played to you at the beginning. So what the astronomer did was, let's represent this amplitude of the temperature variation as how loud the sound is. And let me represent distance scale as pitch. So this is small scale, high frequency, this is low frequency. And you see these harmonics, it should show up in that sound, and this is the sound I'm going to play to you again now, okay? And let's listen to it. The music of the Big Bang, okay? Okay, let's see, is it a little bit more meaningful to you now? Or it's just as unimpressive as before? Okay, so now to actually understand this sound, you would need to do a lot. So remember I told you, the early universe was a soup of hot and dense elementary particles. So there are, depending on time, there are electrons, there are photons, there's dark matter particles. So you have to take all these ingredients.